All right. The speed at which we cut metals is the major factor in determining productivity. And because of that, it's the major factor in determining our standard of living. Is that a true statement? It's a statement. It is truly a statement. Is it a true statement? The speed at which we cut metals is a major factor in determining productivity and therefore our standard of living. Yes, no? If it is true, what makes it true? Yes?
The fact that we can cut the bulk of our infrastructure out of metal?
Okay. So a lot of the stuff that is around us, that surrounds us, stuff that we use every day, stuff that we buy, is made out of metal. I don't know what percentages are. We make a lot of stuff out of plastic too. Could we make any of the plastic stuff without cutting metal first?
No,
Any of it?
no, because
All of the tooling that we use to make any plastic stuff that we use was machined, likely CNC machined. How about clothing? Could we have any clothes without being able to cut metal? We could. Describe them. I could dress up like Thor, right? Get my axe.
you can probably manage linen.
Maybe linen, okay. But certainly not the clothes that any of us are wearing today.
Oh, yeah.
Yeah, okay. Good thing we don't all have to take them off. I mean, I guess we do all have to take them off, just not in here, right? So we can say that our ability to cut metal faster is important to us, right? You ever think about that when you go to the airport, check in, you got to take off like half of your clothes to get through security? What if somebody just started like a nudist airline? Nobody'd be able to hide anything, right? Okay. With that thought in mind, what impacts the speed at which we can cut metal? Yeah. So, all right. So the power of our machine right? Because the power of our machine will indicate what our material removal rate can be, right? So there's other stuff that happens, right? So the sharpness of the tools and things like that. But the power of the machine has a big impact because it impacts our material removal rate, which impacts the speed at which we remove material to make all these things that we then use to make other stuff. Okay, so the power of the machine. What else goes into that material removal rate? Yeah. So, all right, yeah, so we can look at the diameter, but it's our material removal rate, because that's the speed at which we can cut metal, right? If we can increase our material removal rate, we cut metal faster, right? So we get speed, right? Our initial process variables in our manufacturing, right, are speed, feed, depth of cut. And of course, depth of cut includes width of cut, right? And so feed in inches per rev, and this in inches, and this in inches. Those three multiplied together equals Q, or the material removal rate. right? In inches to the third over, this needs to be inches, this can't be inches per revolution, can it? If we want our material removal rate to have time in it, it needs to be inches per minute. If we want to get inches cubed per minute, that's inches per min, not inches per meter. About 36-ish. What is it, inches per meter? Is it 30? I don't know. Who cares? That's not what we're doing now. Inches per minute. So how do I go from, we like to do our feed at inches per revolution or inches per flute, right? If we do inches per revolution, how do I get inches per minute? Yeah. So that's where we get our speed, because we do this in feet per revolution. Or sorry, revolutions per minute, right? So we've got our spindle speed in revolutions per minute, or feet per minute. We can turn that speed into inches per minute, right? We can do that. So if we hold depth of cut and width of cut constant, and our feed per revolution is specified by the tooling manufacturer, and the tooling manufacturer tells us how fast to feed by feed per revolution, if we want to increase material removal rate, what do we do? So we're going to keep these constant because our tooling manufacturer told us what the depth of cut and width of cut for this tool is, right? Right? They've got an AE and an A. What's the other one? It's on the chart. AE is one of them. Width of cut, AEB, something like that. It's on the chart though, right? Depth of cut, width of cut. That's specified by the tooling manufacturer. Feed rate in inches per revolution or inches per flute is specified by the tooling manufacturer. So if those two are specified and we want to remove material faster, what do we have to do if we want to increase Q? We've already picked the tool. We've got to spin the spindle faster so that our inches per revolution gets us more inches per minute, right? If we spin the tool faster, okay. Now, yesterday we talked about changing light bulbs, right? And somebody answered that they didn't say which light bulb they wanted to buy because they didn't know how long it was going to take to change the light bulb. Who was that? Somebody, right? You said that. That was a great observation. This is the same thing with tooling in a machine tool. So we're making the same part all day long. The tool eventually wears out. Would you believe that? The tools that we use in the machine tools are consumable. They wear out. What happens to the part if the tool wears out? As the tool starts to wear out, what happens to the part? So if we, and we're going to talk about this in just a minute, if we're measuring the parts, and so it's a, let's do a turned part because it's one dimension to measure, right? Diameter. If we're making a turned part, and we're turning the outside diameter on the part with our tool, as the tool wears out, because this is our nominal diameter that we're trying to make, right? And so they're not all going to be on the diameter, right? They're going to be scattered around here a little bit. There'll be some spread. Some of that spread will be because of our ability to measure, right? There's some uncertainty in our ability to measure. Some of that spread will be from variations in the process. You go on like that. If you look at that graph and it starts to do that, what do you know? This is one of the things that we do when we control the process with in-process measurements is we make graphs like this. So what does that graph tell you? Yes?
Your tool is wearing out, so it's not cutting.
Your tool is wearing out. Because when we program it, if we've got our lathe here, and we've got our workpiece, so there's our workpiece. we've set our X offset for our tool, right? You guys have done that in the lathe? Have you done that in the lathe? I think you have. Maybe not. But if you've set your X offset for the tool, when you do that, it knows where the tip of the tool is relative to the workpiece, or relative to the center line of the spindle. And then your tool path goes across like this, right, to make this final diameter. As the tool wears out, the tip of the tool gets shorter. But the machine tool doesn't know the tool wore out. So the part gets bigger as the tool wears out. That's why we see this. Now, what eventually happens as the tool wears out? Because it doesn't just get curved away like that. It also gets less sharp. So what also happens if the tool gets less sharp? Yeah. It may leave different surface roughness, or not cut as cleanly is the way to do it. But it may leave different marks on the surface, something like that. But even beyond that, as the sharpness of the tool gets less, so there's more of a radius on the cutting edge of the tool, what happens to cutting force? You can do it with butter. You can do the experiment with butter. What happens to the cutting force as the tool gets dull? Who's used dull scissors before?
It goes up.
Cutting force has to go up. In fact, if we look at the tool here, right, so we've got our tool, we've got our chip coming here like this, right, and so the workpiece is moving that way, tool's here, the chip's flowing up there, right? So we assume we have a sharp tool here. One of the things that happens is as the tool does this on that radius, and that's the radius I'm talking about, we end up with a longer shear plane. If we get a longer shear plane, that means the force had to go up. So, as the tool wears out, the force goes up. What happens eventually if the force keeps going up? So when the force goes up, power consumption goes up, right? Because power equals force times velocity. So when the force goes up, power has to go up. Eventually the machine runs out of power, or the tool breaks. When would we like to change the tools? So we're looking here. When do we want to change the tool? Yep. So one of the cool things is as it's doing this, if we're measuring this is really cool. You guys, when you're making your pistons in the lab, you're adjusting a value in the tool wear column on the tool offsets. So as the parts start to get bigger, you can adjust that tool wear value. And so the part starts to get bigger. You notice it here maybe, so you adjust that tool wear, and you drop it down to here. And then it starts to get bigger, and you notice it again, and you drop it back down. So you can have those parts like this. So you can adjust it in the machine, but remember the cutting forces are going up. And eventually the tool's going to break. When do we want to change the tool? You want to wait for it to break? We want to change the tool sometime before it breaks, right? Depending on if it's screwing up the surface quality or something like that, then we may need to change the tool way back here. Did a consulting job once. It was a surface metrology consulting job. The people make I think these. It's a thing that gets physically implanted in the human body, and so it's important to not screw that up. Because like a permanent thing, like people get these and they stay in the body, and they noted that they had some good parts and they had some bad parts. So they had a functional test. If you're going to implant something in the human body and it's going to stay there, you kind of don't just want to trust your statistics and your ability to control the process. You kind of want to have a functional test. So they had a functional test for it, And they said, we got some that work and some that don't work. We don't know why. That's problematic in manufacturing. If you got some that work and some that don't work and you don't know why. And so they brought him and I looked at it. Very, very technical. Now, I had learned by now that you don't tell them the answer until you have the purchase order. Because if you tell them the answer before you have the purchase order, they never pay you for the answer. But demonstrating my abilities, these are the ones that don't work. How'd you know? I says, now we need to get down to the purchase order time, right? And so I actually had to prove that that was the thing too. I couldn't just know the answer. It's kind of cool when you know the answer and then you prove that you're correct. But no, it's because I could see there was a waviness. Remember we talked about surface roughness last week about this time? And so surface roughness is like the ups and downs on the surface, right? Well, there could be more than one frequency there. So you can have ups and downs like this that look like this. And so if you have that kind of a thing, you've got a waviness. So I see there's a waviness. So it turns out the answer to their problem was changing the tools more frequently. Tool was wearing out. It was getting a vibration in the system that was causing that waviness. All right. So if we want to cut faster, at some point we're going to have to spin faster. Because the tools are designed to feed at inches per revolution or inches per tooth. If we want to cut faster, we're going to have to spin faster. When the tools wear out, what do you think causes them to wear out? When the tools wear out, what do you think causes them to wear out?
If the same way that the tools are cutting the material cutting back on the tool.
Yeah, the material is pushing on the tool, right? Every force has an equal but opposite reactionary force. Something like that, unless we're not accelerating. If we're accelerating, then they don't have to be equal and opposite. So the part's pushing on the tool as the tool's pushing on the part. The chip slides along the rake face of the tool, right? We know that there's friction between the chip and the rake face of the tool, right? We can prove mathematically that there's friction. What happens when you rub? Everybody do this. Everybody that has two hands, do this. Get your hands, put them like this. First, cover them with chalk. It's totally more fun because it's dust and you don't have to do the chalk stuff. Put them like this. Do this. What happened? What happened? Yeah. It's got warm because it's friction, right? Would you imagine that as the chip slides along the rake face of the tool, just after it stopped being workpiece and became chip at that shear plane? So I mean, at the grain boundaries, the chip is sliding along the grain boundaries of the workpiece material too, right? That's that all that energy goes into the shear plane. A bunch of energy gets into the tool from that sliding. Would you believe that the temperatures are high? Extremely high, like you don't want to touch it kind of hot. In fact, has anybody seen a tool that the chip got welded to? You haven't? Oh, they're around. You maybe even did it in the lab and didn't notice it. But the chips will, so how hot does it have to be to weld something to something else? I don't need a specific number. It has to be hot enough to melt the material. When you weld things, the materials melt and become one thing. So hot enough to melt metal. That's pretty hot, right? Who had chemistry? High school, college chemistry. What's the kind of reaction that goes faster if you add heat? If you add heat to the reaction, yeah? Endothermic reaction. This tool wear actually partly is happening because of an endothermic reaction, which means when you add heat, the reaction happens faster. Tool wear happens because of heat. Now, if we rub our hands together like this, they get warmer. But if we do it like this, they get warmer faster, right? More speed means more friction means more heat. Faster you go, the faster the tool wears out. It's amazing. It turns out that if you plot on a log log scale the. All right, let's just look at the graph. Tool life versus speed. I should have known that because speed is the independent variable, right? Speed is the one we choose. You always put the independent variable on the x-axis. If we've got tool life versus speed, we get graphs like this. The log of the speed, the log of the tool life. The different lines that we get are for different material conditions or different tools. But we get this straight line, and it happens all the time. The tooling manufacturers, by the way, don't share this data directly with you as the customer. But this is how they figure out, they tell you what speed to use. So they don't want to use a speed way out here that's going to give you a short tool life. So they pick a speed over here where you get some sort of a reasonable tool life. So the faster we spin, the faster we cut material, the faster the tools wear out. So in our light bulb calculation, if we move that over to tooling, if I can tell you that for the same speed, I can double the tool life, should you buy the more expensive tool, even if it costs more than double the other tool? Yes, you want to buy that more expensive tool. So the factors, and let's do the slide here. So here's some real data. So thermally activated, you can figure out the best cutting speeds. So cost per cut. And so this is not when we're figuring out what's it cost to make one Stirling engine. This is when we're figuring out how fast should we go to optimize the tool life in this situation where we keep making the same thing over and over and over and over again, and we can't possibly make it, we can't physically make it fast enough for our customers. Our customers want to buy it faster than we can make it. We want to do this kind of analysis. And so this is the kind of analysis that MQP I told you about went through and did. They went through and they optimized these things. And so our cost per cut equals non-productive costs. What are non-productive costs? These are the time you spend putting the part in the fixture. Those are like non-productive costs, right? You're not adding value to the part when you're putting the part in the fixture. You're just putting it where it needs to be in order to add the value. So there's that cost of cutting. We had our shop rate, right? So it's the shop rate multiplied by the time of cutting actually happening, or the you might even break it down further than that. It's the cost of when the tool's engaged with the workpiece material. So when you go up to the tool change height and change tools, there's no value being added to the part, right? You're just getting the next tool ready. When you're rapiding from one side of the part to the other side of the part so that you make the next feature, there's no value being added to the tool, to the part. So we have when you enter the machine, you get to your 6 safety steps. What's the last of those safety steps we want you to do? The 6th one. Yep. Check the distance to go. What's the one just before that?
Rapid rate 25%.
In lab, we usually tell you to use 25%, but if you read the form, it actually says reduce the rapid rate. It doesn't say what rapid rate to choose. And so when I run a mini mill, I might reduce the rapid rate to 100%. Because I'm used to running a mini mill, and so the purpose of that, picking a reduced rapid rate, is so that you have a chance to stop it and do that check the distance to go. So that if something's going on, you have a chance. That's why we reduce the rapid rate. So we have in the other room, so where you guys did your Y blocks in there, and I guess you went over and you measured your cylinders in the other room too. So there's that boxy looking machine just as you walk in, it's right next to the robot. There's a lathe, there's a box, and there's a robot there. So that's the mill drill center. It's actually got a pallet changer on it. So you'd be loading a part on one side while it's cutting on the other side, so you can reduce that part changeover times. So that machine, full speed rapid, 2,000 inches a minute. Your mini mill, full speed rapid, 600 inches a minute. So that machine on 25% rapid is like the mini mill on full speed rapid. It also has a high speed tool changer. You can't see the arm move. It moves so fast. It's a mechanical tool changer. Sometimes if the tool's not seated right in the arm, you hear a loud bang because it throws the tool against the side of the machine tool on the inside. You don't want to operate that at full speed with the door open, especially if you're standing in front of the door. Okay, so non-productive costs. The cost of cutting us when the tools engage in the material. We got cost of changing tools. What's the cost of changing tools? What goes into the cost of changing tools? I'm going to tell you not the cost of the tool because that's a line. What goes into the cost of changing tools? Yeah.
Time.
So there's time, right? There's time for the operator to be doing the changing. There's time that the spindle's not cutting because you're busy changing the tool, right? The cost of changing tools and cost of raw materials. So which ones of these have time associated with them? Cost of cutting has time associated with it, right? Yeah. Non-productive probably has time associated with it. Cost of changing tools definitely has time associated with it. And cost of tool, no. Cost of raw material, no. Doesn't have time. Could have time. Yeah. In general, doesn't have time associated with it. So if you get formulas for all these different things, you'd actually get time out and you can optimize for time. And we'll go through that very quickly. If you plot it graphically, you'll find out that there is an optimum speed where you've got, so the cost of cutting comes down, but the cost of the tool and the tool change goes up. There's always a minimum. There's an optimum speed at which to operate your spindle. Yes?
Could you go back to the cost?
The one where we just had this?
Yeah.
Yeah. Oh, you can download this in the lecture notes. You're getting it. You want the next one? Because they're all broken down here. Okay. Perfect. All right, and you can get this. It's in the lecture notes for today. So when should we change tools? Just before the explosion. Arrhenius equation. Arrhenius is the guy that figured out the heat thing and the log plots, and you get these straight lines. He's the he's one of those scientist guys from back in the 1800s. Oh, there he is. Swedish guy. So this equation here will explain these kind of lines here. Cool beans. All right. Oh, amazing. I am 100% right on time to switch topics. I said at 11:30 we're going to switch topics. And look at that. That's the last slide. Ready to switch topics. Okay. If you'll note over here, the objective of today's class is to cover topics we're behind on because the professor talks too much. Cost per cut, we're done with that. Quality metrology, manufacturing. What do we remember about quality? We did quality a week ago, right? Talked about quality a week ago. What's the most important thing you remember about quality from a week ago? What's an important thing you remember about quality from a week ago? This is the whole thing we did the cars, yeah?
Quality is free, relaxed.
Yeah, I didn't say that. That's pretty cool, but I totally didn't say that. Quality is free, the lack of it is expensive. What does it mean to, all right, what does it mean to produce a quality part for your customer? We're talking about manufacturing quality, not the mushy-feely kind of quality.
Reproducibility and reliability.
So we've got some reproducibility and reliability, R and R. But making a quality part for your customer is making the part that your customer wants. I'd actually go beyond that. I'd say it's making the part that your customer needs regardless of the part that they ask for. But in general, in manufacturing, it means making the part your customer wants. They should want the part they need regardless of the one they ask for. And we know what the customer wants because they've given us specifications, right? And our specifications include what? Our specifications include geometric, dimensioning, and tolerancing. Right, so our specs are laid out in our geometric, dimensioning, and tolerancing. The customer tells us what they want. Oh, we talked about the steps that go into quoting a part yesterday, right? So your customer has given you specifications. They've told us what they want with specifications and with GD&T. How do you know that you've given your customer what they want? Or better yet, before you ship it to your customer, how do you know it's what they want? Before you ship it to the customer, it's good to know that it's what they wanted, right? They actually get really pissy if you ship them stuff that's bad. Occasionally, it's okay if you say, we think this is a bad part, but it might work for you anyway, so we're going to send it along with all the good parts. Occasionally, that's okay. But if you just send them bad parts and tell them that we think they're good parts, they don't like that. So what do you want to do before you ship your parts to your customer? So we might want to check the quality. And so when we do that, we call that inspection. When you're quoting the part, wouldn't it be cool to create an inspection plan? Because that inspection has cost, right? That inspection has cost. So when you're quoting the part, an inspection plan might be nice. All right, so quality metrology, manufacturing, we talked about all this stuff. Well, this is pretty cool. If you want to learn more about this stuff, you should check out the ASQ. ASQ gives quality, community, professional certificates, knowledge, blah, blah, blah. According to ASQ, quality is a subjective term. We figured that out, right? Quality is a subjective term. Product or service, yeah, okay, you can read all that stuff. All right, so we're talking about metrology. To measure is to know. If you cannot measure it, you cannot improve it. When you can measure what you're speaking about and express it in numbers, you know something about it. When you cannot measure it, when you cannot express it in numbers, your knowledge is meager and unsatisfactory. Anybody know who said this? Famous guy. Famous scientist guy. It's not Arrhenius. Lord Kelvin said this. They named the Kelvin scale after him, right? He also said that X-rays will prove to be a hoax. When we make our metrology plan, what should we measure? First, let's see, what can we measure? What can we measure? Mm-hmm. True length. We can measure length. What else can we measure? Yep. What else can we measure? Actually, length changes with temperature, huh? Pretty much always. Everything has a thermal expansion coefficient. What else can we measure? So we have to actually measure. In order to know length, we have to know temperature. Mass. We did this the other day, right? Color. We can measure length, temperature. I once built a colorimeter thing for measuring color. They're really hard to do because it depends on the light source. And so if you get any light contamination, you screw up your colorimeter. Length, temperature, mass, color. What else? In manufacturing, what do we want to measure? What do we want to measure in manufacturing? Well, one, we want to measure the things that our customers told us are important, right? We definitely want to measure the things our customers told us are important. What are those typically? Length. Length. Usually the customers aren't specifying temperature. Occasionally the customer is asking for mass, but usually since they've picked the material and they've given you the physical dimensions and the material has a constant density, you could figure out the mass, right? Actually, weighing something may be a way to see if you got some of the dimensions correct if they're hard to measure. But length. Surface roughness, we can measure that. We're going to talk about that in about 5 minutes. Length, surface roughness, parallelism, perpendicularity, so we can measure angles. Those are the things that we can measure. Here, what do we want to measure? You guys have made one of these, right? Did you measure it when you finished making it? How did you measure it? How did you initially measure it when you finished making it? Did you check it with a go, no-go gauge to make sure that it was within the tolerance? So that's kind of a cool thing, right? So we make our gauge here. And so if our part fits over the go side and then doesn't fit over the no-go side, it's within the right range. That's cool. So it tells us if it's in the right range. It doesn't tell us how big it is. It just tells us if it's in the right range. Then how'd you measure it? Use the probe and a machine tool as if it was a coordinate measuring machine, right? The CMM. So you get it measured a cylindrical shape inside there. So you do that. Why do we have to do that? Yeah.
Because even though the part is like the range of the piston that the effort type piston is exact measurement.
Yeah. So we could have had go no go gauges with a tighter tolerance range, right? And then you might not have to measure the cylinder. You could just make all the pistons all the same size. The reason we have the broad tolerance here is actually historical. There used to be a secondary operation on the pistons, which we don't do anymore. But in order for because we make the pistons to match the cylinder, right? Our process makes a piston to match a cylinder. We used to have a secondary operation on those pistons where we put them in a collet, and if the piston was too big or too small, it wouldn't work in the collet. So the reason that we had this broad tolerance on the cylinders was to make sure that we made pistons that would fit in our fixture for that operation. So we could cut that out. Nope, not going to do it. Not going to do it. This is a good exercise. But the reason we started doing it is because we used to need to. But all right, so we can do these things. We measure the things. All right, metrology. All right, surface texture. How do you measure surface roughness? I told you you could do it with capacitance last week. Is anybody like a hip hop DJ kind of guy in the class? Could be. I don't know. People have hobbies, right? But there's those things. They get the things that spin around. You've seen it, right? They put their hand on it, it goes wee 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 wee, right? Right? Except it sounds better when they do it, right? So those things that spin around, those are records. And so the thing that goes over the records is the record player, or the spins it. The thing that moves up and down and vibrates is called the record player needle. That's where the sound comes from. That is sort of the industry standard technology for measuring surface roughness right now. They have a little stylus with a diamond tip on it, like a record player needle. They drag it across the surface, and it outputs a digitized, because we don't do it with analog anymore. We used to do it with analog, and we'd have little circuits inside the machine that would give us a number, calculated number based on the signal that came off. We don't do that anymore. Now we digitize it, do everything in the computer. But it gives us a signal that looks sort of like this. Now, this has got a couple of wavelengths in it, right? We've got a wavelength that we see here. These little bumps are sort of wavy. And then we've got this other wavelength that we see here. So one of the first things that we do when we're calculating surface roughness is we separate those two wavelengths. And so in software, we'll end up with something that looks like this. And something that looks like this. This is the waviness. Remember I said I looked at those parts and I said there's a waviness at about 2 millimeters. I looked at those parts. So I was seeing this pattern on the surface in there. We have our roughness here. And so if I have this, what can I know about it? And so this may still have some other patterns in it. We may not have separated everything completely here. But if I have this, what do I know? Everybody's got a table in front of them, two surfaces on the table. The wooden surface and like a Formica surface. Take your thumb. Put the thumbnail on the surface, move it back and forth. Then put it on the other surface. What do you know? What do you know about the two surfaces? Puma shirt, what do you know about the two surfaces? One of them is smoother than the other one, right? So your thumbnail can actually detect about a 10,000th of an inch up down when you drag it across like that. Your thumbnail is actually very sensitive. Is this a good way to measure surface roughness? So I can do this, and I can do this, and I can tell you that both surfaces, both table surfaces have the same roughness with my thumbnail. So it means I could have one surface that's my calibration standard, and I can test it, and then I can test it next to other surfaces. Is that a good way to measure surface roughness? The US Navy uses it when they're certifying welds in nuclear submarines. It's a method. It's a method. It's certainly cheaper than the record player needle thing, right? So to get one of these record player needle things, like 50 grand. I mean, you can get one for about 5 grand as a handheld one. To get a good one that hooks up to the computer and everything, about 50 grand. What else can we do, though? This doesn't tell us everything about the surface, right? It tells us something about that little spot on the surface that we measured. What if we want to know more about the surface? I mean, we got 1930s record player technology we're using now. Has it gotten better since then? Technology? Yeah. So we could move up to upgrade to CD technology, and we could use a laser to look at the surface. So one of the problems when we do this, let me get some slides here. So yeah, this is what one of those profiles looks like when it comes off the instrument. There's one of the instruments. There you go. That's one of the problems when we do that. You got to keep that needle in contact with the surface. So this is hardened aircraft aluminum that's been measured by one of these stylus instruments, and then a picture taken in the scanning electron microscope. So that diamond stylus actually machined the aluminum part while I was measuring it. So did it measure the surface? What did it measure? Yeah, or something in between the two. What it measured was the interaction of the instrument with the surface. So it's impossible to measure a surface. You can only ever measure the interaction of the instrument with the surface. So if I used a laser to do this, I wouldn't have cut, depending on the power of the laser. Once we were using a laser to measure chocolate, like the top of chocolate bars, and we had to dial the power back to the minimum setting because our laser was actually melting the chocolate. So it depends on the power of the laser, but it shouldn't be cutting the material, right? The problem with an optical instrument like a laser is it depends on the reflections that come back. So shiny surfaces are going to measure different from not shiny surfaces. Shiny bits in not shiny surfaces are going to give you spurious readings. So you got to consider that kind of stuff there. Let's look at parameters. So once we have something like this, oh, and you can measure a 3D map. You can either do it by raster scanning one of these stylus things across the part, or you can do it by raster scanning your laser across the part, or there's this thing called confocal microscopy, where you basically look at the part, and you adjust the focal depth of the lens, and you see when this is in focus, that's at that height. When it's in focus up here, that's at that height. So you look at the focal planes. A lot of different technologies that do this. But these surfaces are, so we've got roughness, waviness. So I talked about roughness, waviness. Lay is the directionality in the surface. So if you got rows after rows after rows, the lay is along the direction of the rows. And we tend to observe it by observing it. We say this surface looks like that surface. This surface looks like that surface. There now are some parameters we can calculate for that. So average roughness. This is, in the United States, the most often used surface roughness parameter. In the United States, average roughness is the most often used surface roughness parameter. We can calculate it on a turn surface if we know the feed rate. We can at least calculate what it should be. Because it's going to be, oh, sorry, this is RT. This is not average roughness. Average roughness is the most used one. This is actually calculating RT, which is the distance from the top of the peak to the bottom of the valley. And this we can calculate based on the feed rate. This equation, and yeah, so here's the derivation of that equation. So RT, again, that peak to valley height that we just looked at, RP is the height of all the peaks above the mean line that goes through the surface. RV, the depth of all the valleys compared to the mean line that goes through the surface. RA, now we get to average roughness. This is the most used surface roughness parameter in the United States. If a drawing says it needs to have a 5 microinch surface, they meant RA unless they told you they meant something else. RA is basically the average distance of each point from the mean line. If you go to Europe or Asia, RQ is the most common surface roughness parameter used. And RQ is basically the standard deviation of each point from the mean line. So these parameters, so what do you know about the surface if you know RA? We have a minute left. What do you know about the surface if you know RA? You know the average distance of each point from the mean line. That's what you know. Those three surfaces could all have the same RA. They wouldn't perform functionally the same way. So we talked about styluses, damaging, there's filtering. Yeah, quality inspection keeps you from shipping bad parts. Process control keeps you from making bad parts. You probably have to do a little bit of each. Definitions. All right, I think we're good. I think I've covered enough of the stuff that I didn't cover before. You'll note on Canvas, I put up a couple of homework assignments. One of them is due next Monday. One of them is due the following Monday. So there are 2 parts in each one of those. There's an A and a B. It's just because it was easier for me to deploy them as 2 parts instead of 1 part. So that's why there's 2 parts for each one of those. So there's I think it's a total of like 8 or 10 questions for each of those homework assignments. So one of them is due Monday next, one of them is due Monday following. This is funny. Oh, it didn't shut off.